Hey everyone, and welcome to This Explainer. If you're working anywhere near the industrial piping world, well, you already know the stakes. We aren't just, moving water to a kitchen sink here. We're dealing with immense pressures, highly corrosive fluids, and extreme temperatures. The difference between a high-performance system that runs flawlessly for decades and a complete catastrophic failure, it usually comes down to one absolutely critical thing: choosing the exact right manufacturing standard. So today, we're going to answer a fundamental question. What is ASME B16.28? And we'll see exactly how this highly specific standard solves one of the absolute biggest headaches in industrial pipeline design.
Okay, let's dive into this. Here's our agenda for today. First, the tight space problem. Second, meet the GHOST standard. Third, short versus long radius. Fourth, tolerances and structural integrity. And finally, the engineering trade-off. Let's get started.
Section 1. The tight space problem. I want you to picture this for a second. How exactly do you pipe a ship's engine room, or say a super compact skid-mounted chemical unit, or a wildly complex refinery manifold? You've got these massive, high-pressure pipelines, and they have to weave through incredibly unforgiving compact areas. It's like a giant, extremely high-stakes puzzle.
In these claustrophobic engineering spaces, you just do not have the luxury of wide-angled turns. Literally every single inch matters. Standard sweeping pipe fittings, they're simply too bulky. And that creates a massive dilemma for project managers who are desperately trying to safely route those corrosive fluids in extreme temperatures without blowing up their physical spatial footprint.
Section 2. Meet the GHOST standard. So how do we solve this? Well, we need to introduce the hero of our tight space problem. What actually is ASME B16.28? Simply put, it's the exact standard for wrought steel butt welding short radius elbows and returns. It strictly dictates the ratings, the overall dimensions, the testing, and the exact tolerances for these heavy-duty steel butt weld components. And let me clarify real quick, it is definitely not B16.29. That standard is strictly for wrought copper drainage fittings. Today, we're living exclusively in the heavy-duty steel world.
But here's a fascinating, kind of wild piece of industry lore for you. B16.28 is actually a bit of a ghost standard. No, really. ASME officially withdrew it way back in 2001 and just merged its contents directly into the broader ASME B16.9 standard. However, engineers and global stockists across the Middle East, Europe, and Asia, they still stubbornly use B16.28 on their RFQs. It survives as the absolute perfect instant industry shorthand to say, hey, I have a strict tight curve requirement here.
Section 3. Short versus long radius. Now, what's really interesting is how our GHOST standard physically contrasts with a classic industry workhorse. To really understand B16.28, we've got to break down the math against B16.9. So ASME B16.9 typically gives you a long radius, meaning the radius is 1.5 times the nominal pipe size, or 1.5D. But B16.28, that's a short radius, exactly 1.0D. So what does that mean out in the field? Well, if you have a 10-inch pipe under B16.28, it has a short 10-inch center-to-face dimension. But under B16.9, that same turn requires 15 inches. That is a massive 33% space reduction, which is absolutely a game-changer for tight heat exchangers in chemical skids.
Take a look at the geometry here. For a short radius elbow, the center-to-end dimension, which is A, is exactly equal to the nominal pipe size, D. This strict 1-to-1 ratio is what allows for a very abrupt, incredibly sharp turn in the flow.
And it's just as impressive when we look at a 180-degree return. For these returns, the center-to-center dimension O is significantly tighter. It's exactly twice the nominal pipe size. This incredibly compact footprint makes short radius returns the absolute ideal choice for densely packed heating coils where space is just, well, at an absolute premium. Section 4. Tolerances and structural integrity.
But here's the thing. Making a tight turn is really only half the battle. We've got to talk about the rigorous rules that prevent catastrophic failure under immense pressure. The standard is packed with dense dimensional tables, and you might wonder, why do these tiny fractions of an inch even matter? Well, because maintaining strict cross-sectional out-of-round tolerances guarantees a uniform butt weld. If these dimensions are off even a little bit, you're going to get uneven weld penetration and highly dangerous stress concentrations. When you're forcing fluid through a sharp 1.0D turn under high pressure, perfect alignment with the adjacent piping is completely non-negotiable.
So, the crucial point here is this hard and fast rule. The wall thickness of the fitting must never drop below 87.5% of the nominal thickness marked on it. Why? Because forming a short radius elbow physically stretches the outer curve and compresses the inner curve, making it incredibly difficult to maintain thickness. In fact, in those localized bent areas, the standard dictates that the metal often must be even thicker just to ensure it safely matches the pressure rating of a straight, seamless pipe.
And this standard definitely didn't just sit still over the years. It underwent a massive safety evolution, particularly back in 1994. The computed proofs test factor was bumped from 80% all the way up to 100%. This literally forced manufacturers to prove, both mathematically and physically, that these tight fittings could handle the exact pipe pressures without a single compromise. To pull this off, manufacturers have to rely on advanced processes like mandrel forming to guarantee that uniform thickness we just talked about, ultimately culminating in highly secure, full-penetration butt welds.
Section 5. The engineering trade-off.
All right, this brings us to our final topic. Let's elevate this standard from just a simple list of dimensions into a critical philosophy of engineering strategy, because choosing ASME B16.28 is a very deliberate choice. First, you absolutely must calculate for the increased turbulence and potential erosion that's naturally going to happen on such a tight turn. Second, you have to choose your connection wisely, opting for B16.28 full penetration butt welds on high-integrity main lines rather than something like B16.11 socket welds, which might leave you with internal pockets. And third, you've got to flawlessly match your metallurgical grades. If you've got a P91 alloy pipe, you absolutely need a P91 short radius elbow so your mechanical properties align perfectly. The whole shebang has to match.
Which leaves us pondering the ultimate engineering choice. Is the incredible space-saving geometry of an ASME B16.28 short radius turn actually worth the physical reality of increased hydraulic turbulence and pressure drop in your pipeline system? It is a robust, rock-solid solution for impossibly tight spaces, for sure, but it demands some serious, careful hydraulic calculation. So the next time you look at a highly congested piping layout, ask yourself, what is the true cost of space? Thanks so much for joining me on this explainer. Keep learning, keep questioning, and we'll see you next time.